Welcome back to the second half of differential equations, where we will actually spend some time looking at the applications of the differential equations and its solution. First example, according to Stats Canada, the population of Quebec was 8 million in 2011 and 8.5 million in 2019. We want to use the standard growth model to predict the population of Quebec in 2025. So, first of all, let us set that time zero to be 2011, and let's express the population in millions so we can actually drop all of these zeros. Having done this, when p is 8, then t is actually equal to 0. So we're plugging this back into p is equal to p0 e to the kt. I get that 8 is equal to p0 e to the k times 0. So e to the 0 being 1, I get that 8 is actually equal to p0. That's going to be my initial population. So now the model can actually be rewritten as p is equal to 8 times e to the kt. Now we need to find the constant k, the growth constant, and for that we're going to use the fact that in 2019 the population will be 8.5 million. Now, there's 8 years separating 2019 and 2011, so that means that if p is 8.5 million, that actually took 8 years from 2011 to get there. So back to the previous equation, p is equal to 8 e to the kt. We replace p with 8.5, we replace t with 8. Dividing both sides by 8 and loging both sides, we get that k is equal to 0.0075781, which gives us roughly a growth rate of 0.76% a year. So the model is now complete, and we get that p is equal to 8 multiplied by e to the growth constant times t. If you're interested in actually finding the population of Quebec in 2025, all you got to do is figure out how many years went by since the beginning, 2011. So 2025 minus 2011 is 14 years. So we replace t by 14, multiplying this by the growth constant, taking the e of that power, multiplying by 8, and what we get is 8,895,403 people in 2025. Another example, example 6. Consider the fact that a researcher finds out that after 3 hours of culture, there are 126 bacteria in her petri dish. When she comes back after 5 hours, she finds that there are 147 bacteria in the dish. So how many bacteria will there be after 8 hours? Another example of a growth model. So what do we know? We know that when t is 3, p is 126. So we put that into the model. P is 126, p0 is unknown, and t is 3. We also know that when t is 5, p is 147. So once again, 147 is equal to p0 e to the 5 times k. Best way to solve that is to divide these two equations. Why? Because the p0s will cancel if we do that. So we divide, and we get e to the 3k over e to the 5k. So 3k minus 5k is minus 2k. So we take the ln on each side, we divide by -2, and we get that it's 0.077075. That is our constant. So we can replace this value into the early equation, and we get that 126 is equal to p0 multiplied by e to the growth constant and times 3 to get the p0. So p0 upon this calculation comes up to be 100. So now the complete model actually reads 100 times e to the growth constant times t. If you're interested in finding the number of bacteria after 8 hours, you simply replace t by 8. So here's your t value. It's 8 multiplied by the constant, e to that power times 100 will give you roughly 185 bacteria. One last example here, more related to physics, this one. The half-life of radium-226 is 1,600 years. That is to say that 1,600 years later, half of the original mass will be gone. So you have a 10-gram sample of radium-226 that you buy for a lab. If left unused, how much of this sample will remain 100 years from now? Well, this is a case not of actually growth, but rather ungrowth, decay. Yet, our standard model can still be used to make accurate predictions. So, adapting a little bit, we're going to denote m for the mass, and we're going to change p is equal to p0 to m is equal to m0. The rest is the same. Because the mass will decrease over time, we expect the constant k to be a decay constant, to be a negative number. So, when the experiment starts, we have a mass of 10. So that means that m is equal to 10 when t is 0. Meaning that if m is equal to m0 e to the kt, then 10 is equal to m0 e to the k times 0. Again, e to the 0 is 1, so the initial mass is 10. We didn't really need to do all this because we knew that m0 at time 0 was given to be 10. So the model actually now reads m is equal to 10 e to the kt. To find k, let us make use of the fact that we know the half-life of this element. So it's known that the original mass of 10 grams will become half of what it was, so 5 grams, after 1600 years. That's the definition of the half-life. So m equals 10 e to the kt becomes 5 equals 10 e to the k times 1600. Dividing both sides by 10, we get 1/2 is equal to e to the exponent 1600k. We ln both sides after making the simplification here. 5 over 10 is a half. And we find a negative number as expected because it's a decay. Minus 0.000433217. It's very small. It's because radium actually decays very slowly. So we now have a pretty complete equation in the form of m is equal to 10 times e to the constant of ln of a half over 1600 times t. If you want to know the mass of a sample after 100 years, clearly you will replace t by 100 years in the equation. Let the calculator do the rest, and you will find that 9.576 grams of the original 10 grams will have survived after 100 years. That completes the application of differential equations. See you soon.